Hi. So today I'm going to talk about dimension hierarchies, and these dimension hierarchies play a very important role in analysis. And there are lots of analysis like the roll up and drill down, which are typically done over dimension hierarchies. So in today's lecture, we'll see how these hierarchies are captured in the dimension tables and what kind of hierarchies we capture. Right. So this tells us about how to model these hierarchies, and as you would see that the hierarchies are of different kinds. Like one type of hierarchy is the fixed depth hierarchy, and the second is a variable depth hierarchy. So there are different ways in which we can handle these. So variable depth again are like slightly ragged, and the other one is ragged. So these are the topics that I have listed, and most of the material for this presentation is based on the book by Kimball. So let me begin by talking about dimension hierarchies and the role they play, and also the type of hierarchies. So hierarchies are present in dimensions, as you know, right? And hierarchies are of different types. You can see there are fixed depth positional hierarchies. So I'll explain that with examples. Slightly ragged variable depth hierarchy. Then you have ragged variable depth hierarchies with hierarchy bridge tables. So that is one approach. And ragged variable depth hierarchies with path string attributes. So this path string attributes approach is not very popular, and also for a first course in data warehousing, I think we will just stick up to this point, stick up to bridge table approaches, right? And we have already covered the ETL module, and so if you have to look at information about hierarchies, so there's a ETL subsystem number 11, which is called the hierarchy manager. So you can go back and look at what this hierarchy manager does. So let me begin with fixed depth positional hierarchies. So it's a series of many to one relationships, and examples of this include product to brand to category to subcategory to category to department. So many to one because many products are there for brand. Many brands can be there in a subcategory. Many subcategories can be there in a category, and many categories can be there in a department. So it is like this always. So these products, say they go up to a brand, and then many brands go up to subcategories, and like this. So it is it is always the other way around. So the arrows are so let me clear this and draw it again. So it is always like this. Many to one. This is many, this is one, and again this continues. So again many, and then to one, and like this it continues. So in fixed depth hierarchy levels have predefined names. So like these are names like product, brand, subcategory, category, department. These are all names, and hierarchy levels appear as separate positional attributes in a dimension table. So these are just attributes, and you can see, once you look at the dimension table, you would understand that how these hierarchies are present in the dimension table. And these fixed depth positional hierarchies are easiest to understand and navigate. Then we have what are called as slightly ragged variable depth hierarchies. So when the hierarchy is not a series of many to one relationships, and the number of levels varies such that they do not have agreed upon names, So we call them ragged variable depth hierarchies. So example, like geographic hierarchies. So levels may vary from 3 to 6. So later in the presentation, I'll be giving you specific examples of the location dimension. So we'll see that how these hierarchies can be modeled, and why we are talking about this levels, and how we model these situations where the levels are not the same, like as we discussed in the retail sales example, like product to brand and to subcategory to category and to departments. So force fit slightly ragged hierarchies into fixed depth positional design. So what we try to do here is that when we try to model slightly ragged, so we try to fix them into a fixed depth positional design, and while doing so, some of the attributes are repeated, right? So wait for the example to come. And then we have the ragged variable depth hierarchies. So here the difference in the levels could be very, very high, and ragged hierarchies of intermediate depth are difficult to support and query in a relational setup. Indeterminate depth, right? So SQL extensions and OLAP tools provide support for recursive parent-child relationships, but are still not sufficient. So I'll talk about all this. And hierarchy is modeled using what are called as bridge tables. So contains a row for every possible path in the ragged hierarchy, and enables all kinds of hierarchical traversers using SQL. Okay, so all these things would be traversals using SQL. So then there is another approach which I said will not be discussing. So I'll talk about this later if we need to. Right now I'm skipping this. So let us now talk about the details of fixed depth hierarchy. So product dimension, we have already seen this, and here what we do is we try to resist normalization and keep the many-to-one relationships flat. So we don't normalize it to give it a hierarchical structure, like we don't break up a table into two or more relations, so that all the information is there in the same table. And similarly, when we talk about store dimension, so there are again multiple hierarchies. One is the geographic hierarchy about the location, and then you have the internal organization hierarchy of the store, right? So these are two different kinds of hierarchies that can be present in the store dimension, and I'll talk about each one of them. So let me give you an example of a slightly ragged variable depth hierarchy. So you can see here that geographic hierarchies, see for medium location. So there are three types of locations in terms of complexity. One is the simple one, the other is medium, and then you have a complex. So what basically here what we have is that in the simplest case, for the simplest case, there is no concept of either a district or a zone. So you can see here, so there is a district and zone in the most complex hierarchy. So cities come together in a district, cities to district, districts to zones, and zones to state, and then to country, like this. Okay, but in the medium level or medium complexity location, there is no concept of district. So what we do is that we repeat this the city information in the district. Okay, and then when we come to the simplest location, so here there is no concept of either district or zone. So you can see we have repeated city twice here. So this is what we are trying to do, that we are trying to use the same number of fields to represent the hierarchy. That is, 1 2 3 4 5 6. So if I say say address, also you count 1 2 3 4 5 6. So we are using 6 attributes to record the address, right, of a particular location. And simple and medium, we repeat the city 3 times in simple and 2 times in city, right, because there is no concept of district in the medium location, and there is no concept of district as well as zone in the simplest location. So for simple location, so that's what city name propagated down to both these attributes. So this is how we handle it. And then if you want all 3 types of locations in a single hierarchy, we have a slightly ragged hierarchy, and the range should be narrow. So the range should be narrow from 4 to 6 levels, and this approach is not recommended if the range is broader, say from 4 to 8 or higher. So if it is say 4 to 8 or 4 to 10 or 4 to 11 or 4 to 12, anything like this, so that then this kind of approach is not advisable, because you would have many city attributes, right, and then it'll be very difficult to convince people that why the city is being repeated so many times, right. And in data warehousing, as I said earlier also, in the dimension tables, your attribute should be well defined, right. So if city appears 10 times, so it is definitely not well defined. So this is how we do slightly ragged. Now let me come to the ragged hierarchy. So I'll first try to give you some examples, and then we'll talk about the solution to ragged variable depth hierarchies. So organizational structure is a perfect example of this. So suppose there is a consulting firm, and there is a consulting invoices data mart that has been designed. So consulting services are sold at different organization levels. So there is a need for reports that show consulting sold not only to individual departments, but also to divisions, subsidiaries, and overall enterprise, right? And the report must still add up the separate consulting revenues for each organization structure, right? So suppose I am a consulting firm, and in this organization or in this enterprise, I am providing consultancy at these levels, right? So how do I handle this? So let us see. And this is another example of a ragged variable depth hierarchy. So I'm trying to talk about parts composed of subparts. So there can be a part which is part 1, which is This part 1, which is comprised of this 3 parts, right? And then this subpart 2 is comprised of part 5 and part 6. Sub 3 is it does not have subparts. And then you have subpart 4, which has another subpart called subpart 7. And like this tree can grow. And you can see very easily that this is a variable depth tree, right? So it is an example of a ragged variable depth hierarchy. And you see here, so this figure has been taken from the Kimball's book. Yeah, and this is the so you have 13 organizations in an enterprise. So named the nodes are named so 1 to 13, and their roll-up structure or the hierarchy in which they participate is shown in figure 7-8. Right? Each organization has its own budget, commitments, and payments. Right? So for a single organization, one can request a specific budget on account using a simple join to the fact table as shown in figure 7.9. So you can see here, so there's a so there's an organization key here, right? And I can, so there's an organization dimension, and there's a ledger fact, ledger fact, and I can do a join to this organization dimension to know the specific budget for an account using a simple join, right? So what if we want to roll up the budget across portions of the tree or even the entire tree, right? So whenever I talk about an organization key, so suppose I'm talking about 13, but I want to talk about not just 13 but everything in this subtree. So how do I do that? Because in this figure there is no concept of organization, or there is no information about organizational roll up in this table, right? So what do we do? So what we do is, so the most standard way to represent, so we'll talk about two solutions. So standard way to represent parent-child tree structure is to use a recursive pointer in the organizational dimension for each row to its, from each row to its parent. Say for example, employee hierarchy. So employee dimension is boss attribute, which is a foreign key to employee itself. So it's a self-referencing relation. So let me tell you what are self-referencing relations. So suppose I have a table like this. So I have an employee ID, employee name, right? And then I say employee boss. So this employee boss has to be an employee, so it will refer to this, right? So for each employee, I would, through this foreign key, I would tell who is the boss of this person, right? So it only tells me about the boss. Now once I go to the boss, then again I'll have to recursively use the pointer to see who is the boss of this person and who is the boss of this person. So what happens here is that if I start with an employee, right, so I go to its immediate boss, so I'll call it boss, okay, right? And then I follow the pointer, the foreign key, to go to the boss of boss, right? So which is, I call it boss square, and then from here I go again to, I again follow the foreign key to go to boss cube. So that means this employee is directly reporting to boss, who is in turn reporting to boss square, and who is in turn reporting to boss cube, and so on. So that's why we call it the recursive key, right, or recursive pointer. And there are functions in Oracle like connect by, which traverses these pointers in a downward fashion, starting at a parent and enumerating all its children. And there is also something called as Oracle CTE, that is common table expressions, is also not found suitable. So the details of that are given in this article by Kimball's Building the Hierarchy Bridge Table, because these kind of recursive pointers are not a good solution. And the main problem is that it is entangled with the organization or employee dimension and depend upon the recursive pointer embedded in data. So the recommended solution that we propose for this is the bridge table that is independent of the primary dimension table. So next what I'll be talking about is the bridge table solution, or the bridge table approach to model ragged variable depth hierarchies. So far what we have done is we have looked at fixed depth hierarchies and then slightly ragged. So slightly ragged can be fixed or can be modeled using a fixed depth hierarchy, provided you introduce some attributes which are not really meaningful, like you need to repeat city in the example that we discussed a couple of times, or 2-3 times in a dimension. So the second approach is that we use a parent-child relationship or a parent-child tree structure, but that also has its limitations because support that you typically find in relational databases is not adequate. Okay, and I strongly recommend that you read this article on building the hierarchy bridge table by Kimball. So there you would actually find SQL scripts written which create these parent-child relationships. So this is what this is one solution that we pointed out in this in the previous slide. So this is how the parent-child recursive design is done. So you can see here that from this organizational parent key, so this is the field, so this just like the boss field, right? And this goes back to the organizational key, right? So so where this organization in a particular enterprise is linked to. So we now talk about the bridge table approach for modeling variable depth hierarchies, ragged variable depth hierarchies. And one of the good things about bridge table is that it is independent of the primary dimension table. So we saw that the parent-child thing that we talked about is not independent. It is tightly entangled, or it is entangled with the dimension. Contains all information about rollup. So that is the second positive point about bridge tables, because rollup information is not there in the earlier solution. And the grain of this bridge table is that each path in the tree from a parent to all the children below the parent is shown in this and is captured in this. So let me show you how it is done. So if you can see here, let me clear the annotations. Okay, so if you see here, so the first column is the primary key of the parent, right? Second column is the primary key of the child, and a row is there for each possible parent to each possible child, including a row that connects the parent to itself, right? And there are other kinds of flags which I'll tell you later. So if you go back to the hierarchy that we had, so one had lots of parents or lots of children, right? So one is so if you look at the first row here, so you can see one is there is a row for parent to parent also, and then you can see there are children like 2, 3, 4, 5, 6 up to 13. So all 2 to 13 are children of 1, because 1 is the root, right? So if I'll take you back a couple of slides, yeah, so you can see here 1 is the root, so everything is a children. So how many rows would be there corresponding to 1 as a parent? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and there will be 1 to 1, so that makes it 13. So you can see if you count these, one, say from here to here, so these are 13 rows, right? And then similarly we start with 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So every node that is there in the tree would be there in the parent organization key. Then apart from this, the parent and the child, we also record the depth from parent. So if I talk about 1 to 1, right, so that means it is the same. So it is, if it is parent to itself, then the depth is always 0. So this you can see from here, this entry, and you can see in all these 3 entries, because it is 11 to 11, 12 to 12, and 13 to 13. Okay, and then the depth is recorded. Then there is also what is called as a highest parent flag. So which means that the particular path comes from the highest parent node in the tree. Okay, so you can see here it is true only for 1, and for all others it is false. So this is also very important. And lowest child flag, so the particular path ends in a leaf node of the tree. So is it the lowest child flag? Lowest child flag means it is it's a leaf node. So I hope all of you understand what is a leaf node in a tree, right? So if it's a leaf node, it's a true. If it is not, it is false. So you can see that I'm talking about, I'll take you back to the, say, 3. So if you look at 3, okay, so it's a leaf node, and so is 5, 6, 8, right? All these are leaf nodes. So if I talk about 1, 2, 3, you can see here 1, 2, 3. So this particular thing, so it is true here. So that's how we model the hierarchies in using a bridge table. So you can see how many rows would be there in this whole table that we just saw. That is the bridge table that we discussed just now. So the calculations are being shown here. So it's the same hierarchy, but only thing is that it is the numbers are not there. So if you look at the total number of records that this bridge table would have, so there are 13 nodes. So 13 nodes to itself, node to node, node to itself. How many? So there will be 13. Sorry, I'll work this out for you here. So this will be 13. Wait a minute. Then there are 12 nodes below root. So root to others, that would be 12. So I'm encircling these. Then below the first level. So below the first level, how many are there? 4 purple and 1, 2, 3, 4, 5, 6 blue. So that makes it 10, right? And below the second level there are 6, and below the third level there are 2. Okay, so if you add them up, 13, 12, 10, 6 and 2, so that makes it 43. So there will be total of 43 records in the hierarchical in the bridge table corresponding to this hierarchy. And then you already know the concept of bridge tables. We have discussed this when we were talking about multi-value dimensions, and this is the table which we just discussed here. And you can see this is the any fact table which requires this rolling up, and then we have the organization dimension. So all the 13 organizations are listed here, and then in this particular roll-up, hierarchical roll-up, there are 43 records. So this is how it looks like, and you can see that the number of records in the bridge table would not be very high, right? Depending on it, of course, depends on the structure of the tree, but it is never too high. So this is how we model the ragged variable depth hierarchies using bridge table. So with that, I come to the end of this particular lecture, and I have deliberately not discussed the path string attribute approach. So if you feel interested in that, you can just read it from the textbook. Nice description is given there, but I think for a first course it is it is fine that we just discuss the bridge table and the parent-child recursive pointer approach, right? And I strongly recommend that you read the Building in the Hierarchy Bridge Table article by Kimball, which is not part of the book, but if you go to the website of the book, you will find a section called as Tools and Utilities, and there you can find this article, right? You can download this article. So with this, I wind up this lecture on dimension hierarchies, and you can see now that bridge tables have roles in not only modeling multi-value dimensions, but also in modeling variable depth hierarchies. So bridge tables play a very important role in data warehousing. Thank you.